The following is a video of a two-part, nearly 3-hour training seminar for SKYWARN weather spotters. It is conducted by Bill Babcock and Glenn Field, who are two meteorologists from the National Weather Service office in Taunton, Massachusetts. Those people who are interested in becoming SKYWARN weather spotters are urged to contact Glenn Field using the info on this slide. The sound quality of the seminar improves quite a bit after the first 15 minutes. This presentation of the seminar begins with a short news story from Boston TV station CBS 4, where meteorologist Mitch Michaels explains exactly what a SKYWARN weather watcher is.
The forecast for now we'll go up to the sky deck, and that's where Mish Michaels has a look beyond the forecast. Mish?
Hey Ken, today are those tame New England weather days. Of course, we know this isn't always so around these parts. In order to keep tabs on extreme weather, we have thousands of trained volunteer weather spotters dotting the state with a trained eye to the sky, helping to keep tabs on all our crazy weather. We call the program SKYWARN. SKYWARN coordinators from across the state met in our weather center last night to discuss our common goal, public safety.
The SKYWARN program here in Massachusetts is one of the best and most recognized programs in the country.
It's a lot of fun. You get to go out, see the weather, see what goes on.
Jim Palmer is one of thousands of SKYWARN spotters across the state, trained by the National Weather Service to report on severe and extreme weather.
A report of a tree down on Maple Street in Danvers. Power lines have come down with it as well.
Hello, National Weather Service.
Reports are sent to the National Weather Service and shared with media outlets like our weather team.
SKYWARN spotters in Massachusetts, there are roughly over 4,800 spotters in the region. About one-third of those are amateur radio operators.
And those ham operators were instrumental in keeping communication lines open during Hurricane Katrina.
We had 90 knots gusting to 120 knots. Over.
I enjoy volunteering. It's a very satisfying.
That's a good feeling to know that we're helping the general good of the public.
Now, these regular citizens who are armed with a keen weather eye literally volunteer thousands of hours each year keeping tabs on our local weather, and we certainly appreciate their efforts. If you're interested in becoming a SKYWARN spotter, free training sessions are now underway across the state. If you'd like to get information on a spot and a time that is convenient for you, visit us online at cbs4boston.com. Live on the CBS 4 Sky Deck, I'm Mish Michaels, CBS 4 News.
Thank you very much, Ken. And good afternoon. I'm used to saying good evening, so good afternoon, everyone. My name is Bill Babcock. I'm one of the forecasters at the National Weather Service in Taunton, Mass. In addition to that job, I am also the office's SKYWARN program leader, which means that I have the pleasure of coming out, especially this time of year, and talking with people about all sorts of interesting subjects like thunderstorms and tornadoes and death and room destruction, fascinating stuff like that, right? And working with me here this afternoon is the ever-talented and lovely.
Right, thank you, Mr. Bill. My name is Glenn Field. I'm the warning coordination meteorologist out at the National Weather Service in Taunton. And the name doesn't necessarily imply that I have to be there for every warning that we issue. My job is to coordinate with all of the emergency managers, the media, aviators, mariners, the general public, school children, police, fire, etc. Basically everybody who's our customer, which is everybody. Have a customer service job. In fact, they were going to call me the service coordination meteorologist. That would be scum, so they stuck with warning coordination meteorologist. Feel free to laugh because it's going to be a very long 5-hour show if we don't laugh. Okay, 4 hours. Well, welcome to both.
And welcome back if you've been on this before, and welcome for the first time for those of you who are rookies. We want both of you.
Basically, the whole reason for SKYWARN, we're going to get into this in much more detail, but for example, for every severe thunderstorm watch or tornado watch we must get at least 5 reports from well-meaning people looking at the wrong cloud feature of funnel clouds. So do we issue a tornado warning every time we get one of them? No. Because we don't want to overwarn, people won't believe us when the real one happens. So that's kind of what, we're also going to talk about winter weather and some other things, but this mostly concentrates on severe thunderstorms and tornadoes and the cloud features associated with them, so we can rely on you for reporting. So I'll just give you a brief synopsis of what we're going to talk about, and we'll go right into it. Basically, we're going to start out talking about who we are and what we do, who the National Weather Service is, Doppler radar, and what SKYWARN is, and then we're going to get you warmed up thinking about storms, thunderstorms, lightning, and all kinds of interesting pictures. And at that point,
we'll move on to talking about in a little more detail the different types of thunderstorms, and most importantly, where in each type of thunderstorm that you can find dangerous weather. And then after that, we'll take our usual, 5-second intermission, I guess.
Generous tonight.
Yeah, enough time to get up, whirl around, and sit down. And just get the blood flowing again. And then after that, we will come back in to talk about weather information. You know, there's a lot of it out there, and the Weather Service is putting out quite a bit. We want you to know where to look to get up to speed if we have a dangerous weather situation evolving. And then after that,
then we'll come back in and talk about communications, how you get our weather information, what we mean by severe, and some other definitions, and then we'll do a quick review of what we've learned about severe weather and how you report it to us. And then Mr. Bill will go into winter weather a little bit, because we also get that around here occasionally.
Once in a while.
And so that's about the synopsis.
And we're going to squeeze all of that into 2.5 hours. Okay, so let us get started then. First of all, Glenn and I have told you that we are with the National Weather Service in Taunton, but just what is the National Weather Service anyways? And what is the National Weather Service? Well, the Weather Service is a federal government agency. We are an agency that is one part of the National Oceanic and Atmospheric Administration, or NOAA, also known as the National Organization for the Advancement of Acronyms.
I thought it meant no organization at all.
That too. Is one agency that is a part of the U.S. Department of Commerce. And so that's where we all fit in. Your tax dollars pay for Glenn and me, and you'll be sorry about that by the end of the afternoon. Hopefully. Our prime mission is the protection of life and property through the issuing of timely weather and river watches, warnings, forecasts, to alert you and your neighbors so that you can take cover immediately and be in a safe spot when that dangerous weather comes through. Toward that end, we have nationwide coverage, and it's not just the Taunton office. We also have 123 local forecast offices. The Taunton office is one of those. Each one of these local forecast offices focuses on its own chunk of the country. And then we also have 11 national prediction centers as well, including the Storm Prediction Center, the National Hurricane Center. You may have heard of them once in a while in the past year. This is how we break up the country. Those 123 local weather offices, everything from Juneau and Fairbanks down to San Juan, and from Guam, all the way up to Caribou, Maine. Zooming in on southern New England, this is how we break up this area. Everything in the light blue is our responsibility from Taunton. And that covers most of Massachusetts, except for the Berkshires, all of Rhode Island, part of northern Connecticut, and also Cheshire and Hillsborough counties, the Keene, Manchester, Nashua areas of southern New Hampshire. Elsewhere, our sister office in Gray, Maine, north of Portland, covers the rest of New Hampshire. We've got an office in Burlington, Albany, and all the way down to Brookhaven, New York, down on Long Island. There we go, right down there. We break up things like that, not because, for instance, we have a thing against Connecticut and we want to confuse them all down there, but just it's all has to do with whose radar, which office's radar, has the best view into that part of the country. That's why we break things up as we do. We have lots of neat equipment that we get to work with as we do our job. We have automated surface weather observing platforms at hundreds of airports around the country, each one watching the weather and putting out an observation every hour, and sometimes several times an hour, as the weather dictates. So this helps us out a lot. We also have weather balloons that are launched twice a day around the country, and from 93 spots total around North America, not to mention 1,000 around the world. These are launched and they measure the temperature, the wind, the humidity, all the way up to some 15 or 20 miles above the ground. Is there a question in the back?
Yeah, the difference between ASOS and AWOS?
The difference between ASOS and AWOS is the difference between the Weather Service and the FAA. ASOS is run by us, the AWOS is maintained by the FAA, and there are certain differences that go into how we go about that. But the basic function of the two is still the same, to take those weather readings, those weather observations. So we have weather balloons going up 15 or 20 miles, and if you want to go up even higher, we have weather satellites, some orbiting the Earth about 150 miles up, others even higher. Those are 22,000 miles above the ground, orbiting the Earth. Now at that distance, it takes one whole day for one of these geostationary or GOES satellites to go around the Earth. Just once, a whole day to go around the Earth. And meanwhile, the Earth is going around once underneath, so the GOES satellites end up parked over the same chunk of real estate 24 hours a day. Every time they take a reading, whether it's an image or a remote measurement of temperature or winds, it's looking down on the same part of the Earth all the time. We also have some high-speed computers down in Washington. Remember back when we were all young, perhaps making models of airplanes or cars or boats or something? Well, meteorologists make models too, but we use high-level mathematics to do our model making. And we run that high-level mathematics on these high-speed computers in Washington. The mathematics, these computer models as we call them, simulate or attempt to simulate how the atmosphere will behave over the next few days. And then meteorologists, both in and out of the Weather Service, look at that information and try to use that to try and forecast what the weather will do. And then we have another fun piece of technology we get to work with. It's called Doppler weather radar. We have these weather radars at all the offices around the country. This is a picture of the one right across the street from our office in Taunton. And inside of it, we've got a 28-foot diameter dish, which is going around and around constantly, scanning the atmosphere. What? Yeah, great. You were going to say something? Oh, okay. Going around, and when I say scanning, what it's really doing is it's sending out a beam of radio energy on a special frequency that likes most efficiently to bounce off of raindrops and ice crystals. So that it sends out the beam of energy. If there's a raindrop out there, it bounces off of it, back to the radar, and the radar is listening for how much of that energy comes back. The more energy that comes back, the more raindrops and ice crystals that must be out there. So the next time you see a radar image, that's actually what you're seeing, a measurement of how much energy got reflected back to the radar. And then we are interpreting that to mean that that energy was rain and or snow or some kind of ice in the atmosphere. And it's not just that there are drops out there and where they are, it's also, in the case of Doppler weather radar, how those drops are moving with respect to the radar. Moving toward it, moving away from it, and that can tell us something about the air circulations as well. In this case, we have a picture taken from our Doppler weather radar. The Taunton radar is way off the screen over here to the right. This is in southern Berkshire County. The red and orange is motion away from the Taunton radar. The green and blue is motion toward the Taunton radar. And you notice this one spot right here, we've got strong motion away from the radar, smack dab up against strong motion toward the radar. In effect, this is an area of rotation. The storm is spinning in this location. And just a couple minutes after this image was made, a large, bordering on huge tornado touched down in the town of Great Barrington, Massachusetts, Memorial Day 1995. Killed 3 people and caused $25 million damage. And the Taunton radar was able to see it 100 miles away. Yeah, at least we were able to see the parent circulation of that storm. So you think
in place, the Weather Service is all set. Perfect forecast, perfect warnings, 24 hours a day, 7 days a week, right? Well, not quite. It's good. I would not toss it away for anything in the world. But it's made by humans, so since humans aren't perfect, obviously the machinery itself will not be perfect either. So we've got to find a way to get around that. Not perfect, you say? This is government technology. It's our tax dollars. It better be perfect. Well, case in point, back in 2003, we had a thunderstorm come down out of the Berkshires into the greater Springfield area. That thunderstorm caused some damage, tree branches down in West Springfield and Holyoke. As it moved over Westover Field in Chicopee, they estimated a wind gust of 58 miles an hour. On both the Taunton and Albany radars, it looked like a garden variety thunderstorm. But on the local television radar, right there in Springfield, it was clearly looking like a very dangerous thunderstorm, one with great potential for producing damage. So what is this? The government radars that cost, what is it, Glenn?
It's only $1.8 million at each location.
Oh, $1.8 million in each location. Chump change, right? In any case, what's happening here? A $1.8 million radar and it missed a severe thunderstorm, but a local TV radar caught it? Well, that has to do with the fact that we are limited by, unfortunately, the laws of physics. A radar beam, for all practical purposes, shoots out in a straight line. Meanwhile, the Earth's surface is curved and curves away underneath. So as you get farther away from the radar site, the bottom of that lowest radar beam gets higher and higher above the ground. But in the case of the greater Springfield area, the bottom of that beam from the Taunton radar is about 6,500 feet above the ground. It's also 6,500 feet from the Albany radar beam. So both the beams are hitting the storm at 6,500 feet. Most of the storm, in this case, this storm was concentrated from about 2,000 to 6,000 feet. So we were missing most of the storm. It was down in the grass, as they say. But the local television radar was right there and was able to scan the storm from bottom to top and get an accurate measurement of exactly how the storm was structured. So that was the problem. It is something that we have to be concerned about, and because of that, because of the imperfections in the mechanical source of information, we have to be able to supplement that with information from other sources. And a very important source is someone who is actually there, able to take measurements, able to tell us exactly what's going on. But even the human is not always going to be perfect, is not going to be able to see everything in the storm. So we need to be able to take the best of both worlds, the human information and the machine information. A term that we have for this is the human-machine mix of information. Take the best of both worlds and you get information that is superior to either one individually. And that leads us to SKYWARN. What is SKYWARN? SKYWARN is you, the civilian volunteer trained by the National Weather Service to report specific weather conditions that we need to know in order to supplement the information we're getting from all of our technology. Things such as wind gusts, hail size, rainfall, and even certain cloud features that tell us about potential developments in the storms we're monitoring. It came about in the 1970s in the aftermath of what's been called the Day of the Killer Tornadoes, a massive tornado outbreak that took place out in the Midwest. It covered something like 13 states, killed 330 people, almost 150 tornadoes doing all this. And in the aftermath, it was determined that where we not just relied on the machine information from radars and from other sources, but also combined that with eyewitness accounts from people who knew what to look for. The combination of those two things allowed us to do a much better job. Now, over the years, SKYWARN spotters, the way to make use of that information has evolved in a couple of different ways. For instance, out in the Great Plains, they have what they call storm chasing. I mean, it's wide open and flat. You can see for great distances in any direction, so you can actually monitor storms from far away, zoom in on them as necessary, but follow their progress fairly easily. And if you want to travel north or south, you can be reasonably sure that the road you're on is going to continue to move north or south for the next half hour. And so because of that, we can just have small groups of people out there monitoring what's going on and reporting back to the local office as to what they see. Here in New England, though, we have these weird things called trees and hills. And as for the road system, well, let's not even get started on that, right? Bottom line is you can't see very well for distance, and if you tried to chase any of these storms, if you could, there's no guarantee that you'd be able to follow it because it's moving in a straight line and you're not. So instead of putting people in potential danger, instead we train a lot of people rather than just have a few, and we have them go about their daily lives, and if some of this dangerous weather crosses their path, they report to us. Just give us a call by phone, by radio, whatever, and let us know what they have seen, and that's that. It's a lot simpler system, and it also works. We're often asked by people getting trained, do I have to have a amateur radio license in order to be a part of SKYWARN? There are parts of the country where they do require it, but there are other parts, including here in New England, where that is not the case. We do think that it's useful if you have it. There are cases where it is useful to have that amateur radio license. For instance, what happens if you have the storm to end all storms come through, knocks down the telephone lines, the power lines, and just to add insult to injury, it takes out all the cell phone towers as well. How are you going to report back that, hey, we have had major league problems, and you should know about that to warn others? Well, how about that battery-powered handheld radio that the amateur radio operator might have? That's certainly an option. So it gives you that extra means of communicating that something has happened. Roughly 1/3 of all of our spotters are amateur radio operators, and by great feats of mathematical deduction, I would assume that that means that 2/3 aren't. Hey, I went to college, everything. Okay, yeah, we have quite a program in the Taunton area. About 4,500 trained spotters here in southern New England. That's one of the largest programs in the country, and we are proud of it as such. We have, as I say, both amateur radio and non-amateur radio folks in the program. We get lots of information, and that has helped the Taunton office maintain a fairly high performance in terms of getting warnings out to people in time for them to be of use. And we have a ham radio station at our office that all the amateur radio information gets funneled in through the various amateur radio nets into that station, and it's just a few feet away from the forecasters, so the forecasters find out about the information they need to know about very quickly. We are able to monitor various frequencies, the 6-meter band, 2 meters, 440, shortwave, and even computer connections as well, through the internet. All in all, it is very impressive, and the gentleman who is my counterpart in the amateur radio community, his name is Rob Macedo. By day, he is an engineer at EMC Corporation. By night, and the rest of the time, he's Captain SKYWARN. It's amazing what the guy is able to do in terms of keeping the weather information flowing as need be, and he also does a newsletter. Glenn, you tell people about that?
Yeah, I'll just say a couple words. I saw how exciting it is to be in amateur radio, and got my license a couple years ago, KB1GHX. But never get a chance to use it because I'm usually at the office. But anyway, Rob Macedo, as he said, is tremendous volunteer organizing this, a lot of the training sessions and throughout the year operating. The way it works is, first of all, how many people are amateur radio operators? Just curious. Okay. About a third or a little bit more. Again, you don't have to be in it, but that dual role can be important, as Bill said. Rob, well, the way it works is during severe weather, we have operators at our station that are right next to the forecasters, and they can see what's on the radar, be seeking out reports from certain areas, and then in those individual areas, we have other net controllers who can filter out reports of, say, it's raining at my house, and the severe reports, and then Rob goes around and collects them from the different net controllers, or they report them in directly to Rob. And so that's just another means of reporting in addition to the 800 number. Now, Rob has been able to put out about 270 email newsletters so far. From our office, with as much mailing as it involves with 4,500 spotters, we're only able to get out one newsletter a year, basically. We're trying to get two, maybe another one coming to your mailbox in the next month or two, called the Prevailing Winds newsletter, where we have a lot of information in there. Rob has an email newsletter, and there's a sign-up sheet right here that we'll just put like right by the projector here during the break, and you can sign up for it if you're interested. There's no spam. It doesn't go out to anybody except for Rob. And every couple of weeks he sends out a newsletter that gives you the latest happenings in SKYWARN program and some activations that might have happened at the office and things like that. So you don't have to be a ham operator to sign up for his newsletter, which now has more than 1,000 people on it. So it's a great way to get our information out.
Okay, yes, that's a lot of organization there to do the job. The bottom line, though, is how well did we do? Well, last year, the severe weather season, fortunately, only one tornado. That was, of all places, in Great Barrington, Massachusetts, which is outside of our area of warning responsibility, but still fairly weak tornado on June 29th of 2005. We had 18 days where there were severe thunderstorms in southern New England. Several busy days. The busiest was August 5th. Overall, the Taunton office was able to warn successfully for 81% of thunderstorms. And most importantly, those warnings led the severe events by an average of almost 17 and a half minutes. So in 17 and a half minutes, that's 17 and a half minutes people had to take effective action to be in a place of safety before the severe weather moved through. That's good, and we hope to maintain that, maybe even improve on it a little bit if we can. But that is the ultimate goal, to warn you, warn your neighbors, so that you have time to take cover and be safe when that weather comes through. Question? When you say warning, is that coming over commercial radio, commercial TV? That's coming over any communication source that we can send it out on. Commercial radio and television is one avenue. We have our own radio service as well that we send information out on, and that's another source through the internet where possible. Just as I say, any way we can possibly get the word out to people so that we can reach the maximum number of people. That is the goal.
Now the word gets to the TV and radio stations, but just so you know, the emergency alert system is a voluntary system. It's up to the radio stations to determine whether they want to broadcast that information or not. The only thing that's like mandatory is a presidential declaration, but it's usually in the best interest of the radio or TV station to announce a tornado warning, for example, in the event that it actually happens and there's big destruction and they didn't announce it. But anyways, there may be a delay. It's up to them whether they want their disc jockey to announce it or whether they want to go out with our automated voice.
Okay, so another question. About 29, just under 30%. Those were warnings that went out, but there was no severe weather that occurred. what we call false alarm warnings. And we're hoping to bring that down. That is actually down from past years, so we're trending in the right direction.
And some of that could just be lack of reporting in certain areas.
Yes, well, it brings up the question about the proverbial tree that falls in the forest and no one's there to hear the crash. Did it make a sound? Well, if we issued a warning and no one was there to observe the damage, did damage really occur? Heavy philosophical thoughts here on a Saturday afternoon. And speaking of thunderstorms, let's get into the thunderstorm process, how thunderstorms get going. May have a quiet day, smoke from the smokestack rising only so far, and then it hits a very stable layer of the atmosphere and can't go up anymore, and so it just drifts along above the ground. But the sun gets to work on the ground, starts heating it up. The air near the ground gets warmer, rises, carrying with it the humidity that it had near the ground. All that gets higher and higher, and as it climbs, it gets cooler, and the moisture in it starts condensing into little drops of water which collect and eventually form clouds. Alternately, something else might happen that day. Instead of the sun heating the ground, you may get this wedge of cold air racing in from the Great Lakes or from Canada, and the cold air is denser than the warm, humid air, and so it literally acts like a snowplow, plows underneath the warm air, force lifting that warm, humid air. The warm air rises again and cools, and the water drops form and collect and eventually form clouds, clouds of which could be those puffy cumulus clouds that we see oftentimes each day, just like this. Now, most days, that's as far as the process gets, and then sun sets and the clouds go away. But some days it goes farther. The air is sufficiently cold above that the clouds keep growing, forming a tower. In fact, we have a very imaginative name for that. We call this towering cumulus. And as the cloud gets higher and higher, those water drops climb above the point where the air temperature is freezing, which means that as it's up in that really cold air, the water drops freeze into chunks of ice. And those chunks of ice bounce around and into each other, and the cloud keeps growing and growing. Eventually, it reaches the top of the lower atmosphere, where the air is very stable above it, and so it doesn't go any farther. And the strong winds at that level blow the top of the cloud material downwind, forming this flat top that we call an anvil. The entire cloud itself is called a cumulonimbus. Here's what it looks like from outer space. You see this thin stalk here. That's the main storm tower. And it is, as massive as it may look from a human at the ground, it's actually fairly small compared with the overall anvil. As that tower hits the top of the lower atmosphere, cloud material is blown downwind. You see it just starting down at those other two spots. Now, we actually have a little time-lapse movie of from satellite imagery showing you this process occurring as the satellite would see. This took place in Iowa a couple of years ago. Look right there. Boom. This is at about every 15 minutes, each step in the imagery. That's what it looks like. If we back up, we can take a look at a couple of the images. Right there. Go forward one. Right there. Okay. Boom. Top of the tower hits the stronger winds, and they blow the cloud material downwind. A couple more popped up right over there. It's quite a process, and it happens every time we have a thunderstorm. That's basically what's happening. Question? Generally, they do move. In this case, it's hard to tell how much movement was taking place. There are times when thunderstorms will stay stationary, in fact. If the mechanism that's causing the air to lift stays in one spot, then your tower is going to stay in one spot. If it's moving, then the tower is going to move with time.
It's hard to tell in that imagery. It looks like it was moving to the east, but kept regenerating in that spot. So in effect, it looks stationary, but they're actually moving.
Okay, another question? The jet stream is current in the atmosphere. That's what moves all of our surface weather along. So yeah, that would have probably been, certainly jet stream or winds associated with it would have been moving that storm along, yes. Here's what the thunderstorm tower looks like on radar. Remember, radar is sending out that beam of energy and listening for how much comes back. Well, in this case, on this picture, the red is a lot of energy being reflected back to the radar, and the green and especially the blue is very little energy coming back. Just really a few drops, comparatively speaking, in this location. A lot of drops right here in the tower. And so it's all jammed into this one narrow tower as the updraft carries the water and ice aloft. So it's jammed in there. This stuff's going to start colliding with each other. And when you get the ice chunks colliding, some of the ice chunks become larger than the others. And those larger ice chunks, they have more weight to them. They have more pull. They tend to steal electrons from the smaller chunks as the two collide into each other. So we get more and more electrons in the big chunks, and meanwhile the smaller ones are getting them stolen. So the smaller chunks become positively charged, the big chunks become negatively charged. And meanwhile that updraft is still taking place, carries those smaller, lighter, positively charged ice chunks into the upper part of the cloud, while the larger, heavier ice chunks that are negatively charged remain in the middle and lower parts of the cloud. So you've got one part of the thunderstorm cloud getting charged one way, the other part picking up an opposite charge. You may even see a slightly positive charge induced at the ground too, which is opposite what's in the lower part of the cloud. Nature does not like differences like this. And so the net result is these sparks of electricity that shoot between two differently charged parts of the atmosphere or between the atmosphere and the ground. This is the way nature equalizes that charge difference. This spark is just like if we walk over to a light switch and go to flip it on and the finger touches a metal plate and you get a zap. Same basic idea. And these sparks, we have a name for it, as you're probably aware. We call them lightning. Lightning's hot, 5 times hotter than the surface of the sun. So as it shoots through the air, that hotness, as it heats the air up, it's going to cause a shock wave that races out, and we hear that as thunder. Thunderstorms are most frequent down in Florida. You've got sea breezes coming in from 2 directions, colliding in the middle. Also lots of warm, humid air to help fuel the storm. Up here in New England, we get 20 to 40 days of thunderstorms a year. That's the average. Not quite Florida's league, but certainly enough to keep us entertained up here. There are several hazards that thunderstorms carry with them, and to tell you all about that, we're going to turn things over to Mr. Glenn. Okay.
All right, thank you, Mr. Bill. Oh boy, we don't want to talk about this one, do we? But we have to. Probably the first thunderstorm hazard, the one that kills most people nationwide, is flooding. And unfortunately, we've just had a fatality, or I think it's 1, but possibly 2 people that were caught driving in flooded waters. You don't want to drive through flooded waters. We try to get that word out as much as we can. It only takes 2 feet of water to give your car a lift.
6 inches if it's a Yugo.
Anybody remember the Yugo? Also, there can be hidden dangers in flooded roadways. This next picture was taken recently down in New Bedford, Massachusetts. You end up being rescued by the jaws of life, for example. Okay, I told you it's going to be a long afternoon if you don't get used to our kind of warped humor a little bit. The thing is, there might not be a road underneath you. This is about to give way because of this big crater underneath it. All you're going to see is water rushing on top of it. This next image is from Montague and Leverett, Massachusetts, back in June of 1996, where we had stationary, what am I saying? Not stationary. We had thunderstorms moving one after another. We're training, like we were sometimes referred to it, one after another. In just a 3-hour period, caused 6 inches of rain. And that was enough in this one particular spot to cause the normally gentle Spalding Brook here to turn into a raging torrent of water, the likes of which the locals hadn't seen since the 1938 hurricane. And what you're seeing is we used to be standing here. I mean, where we're, what am I saying? We're standing here, and this road used to be connected to over here. So it's completely washed out. So as you're driving along, and you just see water rushing by, you're going to drive through and then drop down and away you go. Because there is no road underneath the water. So you can't tell that just by driving. Okay, so stay away from flooded roadways. And the next thunderstorm hazard is lightning. Bill already mentioned that it's 50,000 degrees Celsius. I've never measured it. That's what the book says. But that's hot. Causes thunder. By the way, there's this thing called heat lightning. Sometimes people refer to it. It's really just the fact that you can see the lightning, but you can't hear the thunder. It just means it's too far away. There's still thunder, because that's what the lightning causes from that shock wave. There's cloud-to-cloud lightning. There's cloud-to-ground lightning. Of course, we're most interested in that because we live here at the ground. Here's a great shot of lightning in Duxbury, Massachusetts, and the interesting thing about this picture is that it's outside the rain area. See all the heavy rain here? People seek shelter when it's raining and lightning and thunder, but most of the injuries that occur, and it is the number 2 weather-related killer in the country, next to flash floods, most people are caught by surprise from the bolt from the blue. Sometimes this is just a mile or so, but it could be 10, 15 miles, sometimes as much as 34 miles. That's the farthest documented case I've ever seen, is 34 miles outside the rain area. 1 out of every 8 lightning bolts is outside the rain area. So here's all the heavy rain occurring in this huge thunderstorm cloud, but the bolt from the blue here. So theoretically, in the extreme case, you could be on the beach in Newport, Rhode Island, and struck by a thunderstorm over Providence, for example. I mean, think about that. That's the bolt from the blue. So big implications then for the macho baseball coaches and soccer coaches who say, okay, the rain has ended, so it's time to get back out there and play, right? But it's your duty as parents and even as kids to tell the coach. I know it's not the coolest thing. I used to be a coach, but it's not the coolest thing for your kids to go up and say, but Mr. Babcock and Mr. Field says we should wait another 30 minutes until the storm is safely passed. But that's what you need to do. In fact, there's a couple of catchy phrases that we use. If thunder roars, go indoors. And a second one is, if you can hear it, fear it. And you really should. Is it just baseball? How about football? Anybody heard of Michael Vick? He used to play on the Virginia Tech Hokies. Here it is out in Roanoke, Virginia, and the stadium filled to capacity, more than 50,000 people at the opening kickoff, and a lightning struck 6/10 of a mile behind the stadium. Miraculously, nobody was injured. The game was canceled. But where would you go? You can't hide in these little thingies here. You can't get 50,000 people in there, I know that. Imagine if that was the old Foxborough Stadium with the metal seats. They have these lightning arresters at the top of the stadium, which hopefully would attract it and ground it. New Gillette Stadium has lots of big fancy lightning arresters there with the newest equipment, but lightning doesn't always go to them. It's going to go where it wants. I mean, hopefully it would be attracted to that. Okay. Here's a couple, several people that were struck by lightning at the U.S. Open. I don't believe any of these people were killed, They did recover, but a lot of people are killed by lightning. I'm not a medical expert, but it amazes me how you can be revived by mouth-to-mouth resuscitation, because in a lot of cases, well, lightning likes to travel along the outsides of objects, like humans as well. You can often be revived by prompt mouth-to-mouth resuscitation. Just be aware that lightning does like to strike twice in the same location. That's a myth, that it doesn't. In fact, the Empire State Building gets struck 30 times in a row sometimes, because once it's dug its channel through the atmosphere, it's very easy to come through that very same channel again. So just be aware that there could be another lightning strike in the area for your own safety. And they don't carry an electrical charge, so it is safe to touch people that have been struck. But just now, a little digression for a couple minutes and a commercial advertisement. Some of you may have heard of Dr. Mary Ann Cooper. She's the leading, at least in the country and possibly the whole world, medical expert on lightning. And the statistics for lightning injuries are way underdone, because a lot of people that are struck, not a direct strike, but if it strikes the field and you did get some sort of a strike from it, you say, oh, I'll be okay. And then you don't go to the hospital, many cases, decline treatment, but a week later, you're having sleeplessness and nervousness and can't remember things. Sort of sound like I'm talking about myself, but I haven't been struck by lightning. But anyway, the thing is, so you go to the doctor and the EEG is normal, the EKG is normal, the blood tests are normal, and then a month later, you're still not feeling right. 5 months later, you see more doctors, and they tell you to see a psychiatrist then. and then 2 years later, they end up at Dr. Mary Ann Cooper's office at University of Illinois in Chicago. And this is where she's seen the extreme lightning cases and done a tremendous amount of research, has shown us some pretty interesting, sometimes graphic pictures, but really helps illustrate. Like, for example, a lightning strike causes the cigarette type of burn. Doesn't cause like a major electrical fire where your whole body's burned. You see a little cigarette burn, and sometimes where it exits out the foot or for something like that. And also causes a fern-shaped pattern in the capillaries that burst and things like that. So years of research, she discovered that there's a little dot under a lot of people's arms, a little red dot, and she took her a long time to figure out that that's just from the acrylic seam of the t-shirt that melts. Okay, so anyway, very fascinating things, and she's going to be coming to our Southern New England Weather Conference. That's the commercial advertisement. Has anybody been to our Southern New England Weather Conference? Yeah, a couple of you, great. Mark this down, the 7th annual one will be on Saturday, October 28th in Brookline at the Dexter Southfield School. It will be on our website, and you can register for it shortly, but it's a tremendous day from 8 a.m. till 8 p.m., chock full of famous weather people. Dr. Mary Ann Cooper will be there. We also have Professor Kerry Emanuel from MIT, who's very famous for the hurricane global warming debate recently. We have researcher from University of Florida, Dr. Bob Hart, to talk about some of the modeling that we use, bizarre rescues on the Gulf Stream. We have TV meteorologist panel discussion, a whole lot of different topics. Elliot Abrams from AccuWeather will be there. A lot of different things, and very interesting. It includes breakfast, lunch, and dinner, and an astronomy show at the observatory there, all for the low, low price of about $75. And that's, you'll find that that's well worth it for a conference of that magnitude. One other thing just thought of is Mike Utley. You may have seen him. He was struck by lightning on Cape Cod at a golf course in Pocasset, and he really was struck. He had a direct hit to the head, was in a coma for 38 days at Brigham and Women's Hospital, and when he woke up, he was, for the next 2 years, in tremendous pain as every nerve was regenerating. But today, 6 years later, he's playing golf better than ever, walking without a cane, and has become the champion for lightning safety across the whole nation, and the Weather Service in particular, trying to get the word out. And he's devoted his entire life now to figuring out why he survived, because he really shouldn't have survived with a bolt like that. And so new research that's being done out in Cambridge, England, shows that some things that you would never think about, like wearing a metal jewelry around your neck, could save your life. It's possible that it flashed over from his head, enough of it, I mean, he was in a coma, so it was pretty bad, but enough of it flashed over to the metal to have possibly redirected some of the energy. And being wet, sweaty, also attracts lightning, and maybe along the outside surface of the body more so than a direct hit. Anyways, fascinating subject. I already talked too long about it, but anyway, that's another thunderstorm hazard that's very, very important. Hail forms in a thunderstorm as the supercooled waters get lifted up by the updraft of the storm, and it freezes and then comes back down and melts and then gets blown back up again and freezes and melts and freezes and refreezes until it gets big enough that it falls down through that updraft and down to the ground. So therefore the size of the hailstone is directly proportional to how strong that updraft is to sustain it up there until it falls down. We like to refer to things in terms of money, as you'll find out. So this is a $20 bill size hailstone, very, very powerful hailstone. If you cut a hailstone in half, you'll see the concentric circles, almost like tree rings, of every time that storm has frozen and refrozen through its journey through the cloud. In New England here, our largest hailstone is 4 inches in diameter. That's pretty big. Out in Sebago, Maine, June of 1986. On the North Shore, the largest one in southern New England, 3.5 inches in diameter. That's pretty big too. A baseball is 2 3/4, to put it in perspective. The last baseball-sized hail we had was in Brockton in 1999. Prior to that was Richmond, Rhode Island in 1998, and Ellington, Connecticut in 1995. So 3 times in the last 10 years we've had baseball-sized hail. Last year we had 2-inch diameter hail out in Chicopee, getting up there. The statistics show a lot of storms out, a lot of large hail reports in western and northwestern part of the area, and on up into the northeast a little bit, not nearly as much in the southeast where we have the influence of the cooler Atlantic waters. The storms tend to die out as they get into the southeast. And of course, we have spotters reporting hail now, and with all kinds of digital cameras, and they can email us as well. And so here's some interesting pictures. This one we'll never forget. At 3 in the morning, from what's called a supercell storm that maintained itself all the way from the Poconos across northeast Connecticut into southeast Massachusetts, and produced large hail and damaging winds all along its journey. How about this one? This is in the middle of summer in 1992 out in Holyoke, knee-deep in hail. That's not in the winter, that's summer. And straight line winds, another thunderstorm hazard, or downburst as you call it. See the rain coming down very forcefully, and this cloud being kind of like a snow cloud coming down and actually wrapping around, call it a roll cloud or a shelf cloud, the leading edge of a downburst. Every thunderstorm has an updraft and a downdraft. A downburst is a really, really strong downdraft. Okay, and there are some reasons that can cause that, like the strong winds in the upper atmosphere actually being ejected down to the ground, or another reason is evaporation into dry air of that rain. When you step out of the shower, your skin feels cold because evaporation is a cooling process. Well, as the rain falls, evaporates into the dry air, it causes that extra little momentum to come down. The highest downburst was 175 miles an hour in Morehead City, North Carolina. That's the highest that was ever measured. That's pretty loud, pretty strong, right? It's going to cause a roaring sound, or it sounded like a freight train. That's my favorite. Doesn't mean it was a tornado, just a very, very strong downburst. Can cause airplanes to stall and crash. Heard of the term microburst? A microburst is a small downburst in terms of aerial destruction, and a macroburst is a larger downburst. The downburst is the generic term. While we're on that topic, here's the typical damage from a downburst. Does it have to be, what if your trees are twisted, or twisted road signs? Does that mean it was a tornado? Could be the initial attack of those downburst winds, right? What if the center of gravity of the big oak tree was leaning over to begin with, and then it gets hit by downburst winds? It's going to make it twist. How about the tops of the trees being completely sheared off, even down to the middle of the trees, let's say? Also, could be a tornado, could be the initial attack of those downburst winds, just slicing it in half. And again, a roaring sound. So remember, as we're going to train you a little more this afternoon, we want you to report what it is that you see. Okay, not what it is you think it must have been. Okay, so don't report a tornado if you have 175 mile straight line winds if you didn't see the tornado. Okay, that would be straight line winds. That's for us to figure out after the fact what kind of damage it might have been. Here is an example of 104 mile an hour winds down in Brockton in 1996. Caused tremendous amount of damage. And straight line winds have the same kind of statistical frequency, a little bit more into the northeast, but generally the very interesting one that we'll talk about later. But anyway, typical tornado kind of day, if you have southeast winds near the ground, let's say, gusty wind, 20, 25 miles an hour. And if you're lucky enough to see some mid-level clouds on that same day, you'll see them coming from the west or the southwest. Now, it doesn't have to be southeast becoming southwest or west with height. It could be northeast becoming south with height, but some kind of clockwise turning in the atmosphere with height is very important for the development of a tornado. And not only that, but really strong winds aloft. So that what the combination of those two things does mathematically is create these horizontal rolls near the ground. So it's sort of like, if you can see this pen that I'm holding, it's kind of rotating clockwise, parallel to the ground, sort of like a tube of paper towels, for example. Now that's not the direction that a tornado goes, but when the updraft gets going and lifts that into the vertical, take a look at the next picture there. You see these tubes get stretched, and all I'm doing is turning this into the vertical, and look what happened. It turned from clockwise to counterclockwise. See that? A little magic. And anyway, a lot of complicated mathematical equations that go into that, but this tube gets going, and then as a skater pulled his arm in to go tighter and tighter, it's called the conservation of angular momentum, this comes down and from a particular cloud feature called the wall cloud, and the tornado would come out of that in this type of situation. So anyway, that's one way that a tornado can form. And we certainly get our share of tornadoes here. It's not the Midwest, but they do happen here in southern New England. Of course, the granddaddy of them all, the Worcester tornado, 1953. It's been 53 years since we've had a tornado the strength and size of the Worcester tornado. That looks like the Midwest, right? It was on the ground for 1 hour and 24 minutes without lifting up. 94 lives. There's a book out called 84 Minutes, 94 Lives. 1,228 people injured. 10 football fields wide, 1,000 yards wide. And started out by the Quabbin Reservoir and near Petersham, ended up well southeast of Worcester, almost in Norfolk County, and 46 miles on the ground. That's unbelievable. The last F4 tornado, 3 bordering on 4, was in Great Barrington, Massachusetts. This 4x4 was driven right through the car, ended up right there. This was almost the 4th fatality. You see what happened. It peeled back the foam rubber seat cushion of the passenger side, which slowed it down just enough so that the woman sitting there was not perforated. It's pretty hard to believe. I mean, there's the steering wheel. Now, this is Massachusetts, not Kansas. And even in downtown Providence, in 1986, an F2 tornado went through and destroyed the YMCA. And we've had other ones around, including the Windsor Locks tornado in October, of all things, back in 1979. Recently, in 2004, we had a 6-mile long tornado go through Rentham, fortunately just an F1. Is there a question back there? Well, actually, this is the one that we mentioned at first, and then we did show that there was one last year there that was an F0. No, that's just bad luck. But the Berkshires do attract tornadoes, though, being at a higher elevation and a little bit farther away from the influence of the coast. So there is a higher frequency out the farther west you go. We've been talking about the Fujita scale. Everybody's seen Twister? Yeah. You know that an F5 is the finger of God, right? And anyway, starting February of next year, there's going to be a new scale called the Enhanced Fujita scale, the EF scale. And some real famous researchers have all gotten together along with wind engineers, and so they have really looked at this in depth and figured out that this old scale was way overdone for the type of damage that was seen. In other words, F5 damage didn't have to be 300 miles an hour, only 200 miles an hour. So they've lowered the scale tremendously, so a new EF starting next year, anything over 200 miles an hour is an EF5. But they're not going to go back and classify or reclassify any of the older storms. On the other end, they discovered that an EF0 required 65, not 45 miles an hour winds. So but that's the only place it was raised. Most of this was lowered substantially. So an interesting fact. And the new scale has more damage indicators, like an actual chart that we can go down and look at. What was it a farmhouse? Was the sidewall damage? More objective things that classify it. Fortunately, most tornadoes are weak. 74% of all tornadoes are the F0s and F1s. They're generally shorter lived, but they can cause damage. This is an F1 tornado that affected the Cheshire Fairgrounds in Swansea, New Hampshire, in 1997. But it's made out of aluminum and wood, so that's not going to make for an F5 tornado on the scale. 25% of all tornadoes are the strong F2 and F3 tornadoes. They last a little longer, can go 10 to 20 miles on the ground. Notice it's occurring in the partly sunny, rain-free cloud area behind the storm that Mr. Bill's going to talk quite a bit about in this particular case. And not to pick on New Hampshire or anything, but there was an F2 tornado at the Great Brook Middle School in 1998. And the F4 and F5 tornadoes, those are the violent tornadoes, like the Worcester tornado. Fortunately, only 1% of all tornadoes are the violent ones, but they account, though, for 70% of all deaths. So very, very dangerous. In this case, this was the Wichita Falls, Texas tornado in 1979. People that were out fought to seek shelter in a bank and actually went into the bank vault. And that was the smart thing to do because that was the only thing left standing, was hiding out in the bank vault. And we already talked at length about the Worcester tornado, so we can move on there, but unbelievable photograph. In New England, most of our tornadoes are weak, generally less than 100 miles an hour in general. Most of them occur in June, July, and August, but I already showed you Great Barrington in May and Windsor Locks in October. So they do happen at different times. Mostly from 3 to 6 o'clock in the afternoon during the peak heating, but they can occur at other times. And again, in that mini tornado alley, which is most of western Massachusetts, central Massachusetts, a little bit up into the northeast, and western Connecticut, southwest New Hampshire. And we have averaged 1.5 per year in the last 10 years across our forecast area, although a longer average is about 2.5 per year. In, next one. Massachusetts, this is back to 2002, so you can add a couple more on there, like the Rentham one in Norfolk County is up to 8 now, but in general, Worcester County is a huge county, 36 in the last 53 years. Okay, so that's about one every year and a half in Worcester County, but if you divide it in half, because it is a big county, you get about 18, which fits more with the statistics around here. About 18 in 53 years, about one every 3 years, roughly speaking. The last one in Middlesex County, this is Middlesex County, right? What's the last one on the list in Middlesex County? 1986. That's 20 years ago. What am I implying? Okay. Well, it's been 53 years since the Worcester tornado. It's been 20 years since any tornado in Middlesex County. It's been 52 years since the last major hurricane. That's a whole other presentation, by the way. But Hurricane Carol and Hurricane Edna in 1954. And we haven't had a Category 3 hurricane in New England since then. 52 years. Another commercial advertisement. If you want to see about the realities of New England hurricanes, actually Monday evening we'll be giving a presentation at the New England Aquarium. So anyway, there's a lot of commercial advertisements in this. Floods and flash floods, 135 people on average are killed nationwide. This is a 30-year average, but this doesn't include things like Katrina and Rita. Lightning is number 2 killer, 85 deaths. Tornadoes number 3, and hurricanes 25. But again, these statistics are going to change after a couple we had last year. So now we turn the presentation back over to Mr. Bill. He's going to really give you the meat of the presentation, and then we'll take a break. But this is really the most important thing, the 4 types of thunderstorms. And you feel free to take notes. But by the way, there will be at the end, when we give you your spotter identification card, you'll also get 2 glossy books. One, you have them handy, or they're out there? Yeah, they're outside. Anyway, one is, well, they both have a lot of the pictures that you'll be seeing in this. So later this afternoon, when you feel like going over some more, you'll be able to.
Maybe take that hot bath after the end of the day.
Tonight, look over the cloud features again.
Okay, thank you very much, Glenn. And so let's talk a little bit about thunderstorms, specific things about thunderstorms. There are 4 types, 4 basic types of thunderstorms. And you can get sometimes some thunderstorms that sort of fall halfway in between, but just to categorize them for those purposes, 4 basic types. Here's one, the single cell. Single cell, this is a single updraft. This is a single updraft, such as what we were talking about earlier. The water and ice is carried aloft. It is carried high up into the cloud. And in this case, as it hits the top of the lower atmosphere, well, you can see that the anvil, it's kind of spreading out in every direction. That's telling us that there's really not a lot of wind up there, or certainly no organized wind, so that as the top of the cloud hits that top of the lower atmosphere, it's spreading out in all directions, sort of like a mushroom. Now, most times you will see the anvil moving out in one range of directions at least, so that it's usually not on all sides, but certainly visually, if you see this happening, you know this thunderstorm, the water and ice in the updraft is not going to be going very far. And with most single cells, it collects until finally there's so much weight of water and ice that it's too much for the updraft to be able to support. And so that water and ice collapse, frequently down right through the updraft, cutting it off and killing off the storm. And in fact, that's what you can see up here, water and ice collecting. After about 10 minutes, you get too much up there for the updraft to support, and it collapses, and that cuts off the storm, and the storm dies. Now, sometimes there's just enough motion in the atmosphere in the upper part of the tower that it pushes the water and ice a little ways out of the updraft, so that when it collapses, it doesn't cut off the updraft from its supply of warmth and moisture. In that case, the storm may, when it collapses, it'll come down with a thud, some wind, maybe some hail, and then what's left of the updraft will regenerate, and the storm will grow again, perhaps get a little stronger this time. And this could happen over and over, a process we call pulsing. In fact, we sometimes call these pulse thunderstorms as a result, with the storm growing, then collapsing, growing, then collapsing over and over, and perhaps getting stronger with each cycle. So that eventually, it could be holding enough water and ice aloft that when it finally collapses, it will collapse with a resounding thud that could bring in a strong burst of wind that could cause damage, could be bringing down some large chunks of hail that could also be causing damage. And just a picture of one of these collapses taking place. So single cell thunderstorms, brief isolated downbursts, some hail, some weak tornadoes. The process can repeat itself several times like a pulse. The location of any damaging weather is going to be in the immediate vicinity of the storm, either right under it or certainly quite close to the location of that tower. The storms themselves generally last 20 to 30 minutes. With a pulse thunderstorm, that would be about 25 minutes per cycle over the course of a couple of hours. With single cell storms, by and large, they are sufficiently short-lived that if you called us up with a report of some damaging wind, for example, the storm is probably just about done by the time that we're getting your report. That's how short-lived they are. So we may not be able to issue a warning for the specific storm that you're alerting us to. However, we can be using your report to gauge the atmosphere, or some might say read the room. And that can give us an idea of what we need to be looking for with any following storms. Well, if this storm over here produced damaging winds, look at this storm over here on the other side of the county. That one's even more impressive. Let's warn for it right now before it collapses. That's how we can use your information in the case of a single cell storm. Question? Generally, a single cell storm, you might be looking at 5 miles, maybe 10, but generally it's on the order of less than 10 miles in size. These are fairly localized. It's a single updraft.
And we say weak tornadoes and never say never, but it's really not the setup for it.
Okay, so that's the first type of thunderstorm, the single cell. Now we have the next type of thunderstorm set up, the multi-cell or cluster of thunderstorm cells. This is where you get multiple single cells working together cooperatively to help each other become better, stronger, faster than they otherwise might have been. The general diagram here, you can see one cell is pretty much collapsed and there's no more updraft to it, so it's shrinking and the winds aloft are dispersing what's left of the anvil. Whereas the outflow from that has helped the next storm to grow, and now it's collapsing, and as it's collapsed, its strong winds hit the ground and shoot out. They're snow plowing underneath cell number 3, which is still growing, and it, in fact, because of that extra oomph from the wind that's undercutting it, will be able to support even more water and ice than it otherwise might have. And this process goes on as number 2 collapses, number 3 grows to its maximum height, then it collapses and its outflow races underneath storm number 4, which is still growing, but in 15 or 20 minutes, it may be the storm to be concerned about. One thing to be certain about is your strongest updraft, and therefore your strongest storm, is going to be the tower that is tallest. That kind of makes sense. The updraft that is strongest is going to push its storm highest up into the atmosphere. Cells number 1 and 2 have lost their updraft. They're collapsing. They're being dispersed. So they're flattening and getting lower. 4 and 5 are still growing. They're still puffy, but they're much smaller, and they're just getting their act going. Number 3 in this picture is the most dangerous one right now. The outflow from it, though, will make the next one, the dangerous one, in 15 or 20 minutes. Now, if you see lines in the sky, you should definitely report those to us right away. And you can tell this is a government operation. If we go back to the first one, 1, 2, 3, 4, 5. So here we have 1, 2, 3, 4, 5. Your government tax dollars at work. But the process, the important stuff is still the same. Which one of these is the tallest cell? Anybody? Number 3. So what can we say about that one? That's the one to watch, exactly. That's the most dangerous one right now. And how about 15, 20 minutes? Number 2, still puffy but growing. Number 4, it's flattening, it's shrinking, it's dispersing, its history, and 5's even worse. Now, obviously here in Massachusetts, we're probably not going to have this kind of wide open setting in which to view the storms, but this gives you an idea of the basic structure, the basic organization, so that if you see something like this, you know what you're looking at. Multi-cell cluster storms, strong downburst winds, large hail. Again, never say never, weak tornadoes, but again, not the greatest setup for these for tornadoes to take place. And the location, as with the single cell, it's going to be near that most mature cell, the one that's strongest at the time, whether from straight line winds from its collapse or maybe some large hail. That's what you're going to be concerned about. Okay, 2 down, you're halfway there. Here's number 3. This is also a multi-cell setup, multiple thunderstorm cells. In this case, though, they've organized into what amounts to a straight line. The multi-cell line storm, I guess you could almost call it. Here we have 1, 2, 3, 4, 5, just lined up in a straight line here. And the winds aloft are pushing them along either at an angle or straight in into the warm, humid air, which is ahead of it. And so any of one of these downbursts bring the rain-cooled air down to the ground, as you might be able to see over here on this side diagram. The rain-cooled air hits the ground, and it races forward into the warm, humid air. And as it runs into the warm, humid air, well, as we mentioned earlier, the cooler air is denser, so it plows underneath the warm air and force lifts the warm air higher up into the storm. That warm, humid air supplies the moisture that keeps the storm going in the storm. The most violent lift would be right over the leading edge of that rain-cooled air, and it would also be drawing on some of the higher humidity of that rain-cooled air. The result being we get this wedge-shaped cloud right over, literally right over the leading edge of the rain-cooled air. And this wedge-shaped cloud is what we call the shelf cloud, an important feature for you to notice with squall lines. Here's a radar picture out of Oklahoma City. Remember, with radar, it's where you have the most radar energy being reflected back is where you get the rain and hail. It's all concentrated right there, the red and yellow especially. But notice, we have just out ahead of all of that, this area of light blue. Some sprinkles maybe? Well, actually, that is the reflection off of the water drops in that shelf cloud that's marking the leading edge of rain-cooled air. So you can see actually with this picture that the winds in the squall line, the burst of straight line winds is out ahead of the rainfall. And a lot of times that is exactly what you see. You'll get the burst of winds first, then there'll be a gap. It may be 1 minute, it may be 5 minutes, it may be 15 minutes. And then you'll get into the rain and hail after that. First thing you would see would be the ice crystals of the anvil as they thicken and cover the sky. Eventually, you would start to see a darker cloud lower to the horizon, close to the ground, right in there. That darker cloud, that thicker cloud, is the shelf part of the cloud. That is actually the shelf cloud that you're seeing that's approaching. And as it gets closer, it could take various shapes and sizes. The principle is still the same, though. It is your visual marker of the leading edge of the rain-cooled air. And as it moves overhead of you, that is when you can expect the strong winds to form. Here's an edge-on view of the shelf cloud. Rain-cooled air hits the ground, races forward, plows into the warm, humid air, which is force-lifted, and here's your cloud right over the leading edge. As this cloud moves overhead, you're going to get a strong burst of straight-line winds. And notice, too, the wedge shape to this cloud. Also that the point of the wedge is actually pointing away from the rainfall, and in the direction the storm is moving. Important points to remember. Remember this about the shelf cloud. Shelf cloud comes with a squall line. It is at the leading edge of the storm. It points away from rainfall. Remember those points because we're going to give you a contrast to that when we get to the fourth type of thunderstorm. And I don't know, Glenn, what are these things down in here? I don't know, should we get the tornado warning out right away, you think?
Looks like a tornado to me. What do you think?
Well, it's not really attached to the cloud up here, so it looks like it's just a piece of cloud fragment drifting away underneath.
Does anybody know what that's called? Ooh, fractocumulus.
Fractocumulus, hey.
No,
that sounds scientific. It's also good.
We got a four-letter word for it, though.
Scud.
Yeah, very good.
Excellent. These are scud clouds, cloud fragments that are generally independent of the cloud above it. And since we don't have any Patriot missiles, we just have to let them float along uninterrupted. Okay. Any one of those individual thunderstorm areas in the squall line could produce a locally stronger burst of wind. Maybe one of those jets that Glenn was talking about feeds into the storm and brings strong winds down to the ground. Or maybe we get a little extra evaporation because of some local condition. In any case, you might get a strong burst of wind pushing out one part of the line until it forms sort of a bow shape in that straight line. Well, that can tell you right away that the strongest straight line wind in the line is right there at the head of the bow, because that's where the greatest pushing of those straight line winds is taking place. So you get this bow shape, what we call a bow echo, if we are looking at the radar. In fact, this is looking down from above. This is assuming, say, you are floating along in a balloon in the middle of the thunderstorm, but looking straight down from above, and the forward motion of the storm is towards over here. The storm is moving away from over here, so you're looking basically straight down.
But this is like a radar view. This is like a cell on the radar.
Yeah, so you might have north, south, east, west, and you're looking down from above. That's how this diagram would be structured. Yeah, same idea as looking at a radar, too. In fact, let's look at a radar. Here we have our old friend, the squall line in Oklahoma, and if we zoom in on this part of the line, we can see that it bulges out in this point. It's straight on either side, but a particularly strong burst of winds pushed this part of the line out ahead of the rest of the line. Your strongest straight line winds will be found at the head of this bow, because that's where it's being pushed the strongest. And in fact, in this picture, in this image, it's actually just about caught up with the leading edge stuff over here. And there we have Godzilla climbing across the screen right there. I tell you, Doppler radar is good. Question? Squall lines in New England, we have gotten on a couple of occasions measured winds of 104 miles an hour.
Yeah, that was a picture of that storm in Brockton, Massachusetts. Coincidentally, in Worcester.
Yeah,
the Brockton one was more isolated, I think. But
it was a little more isolated.
The one out on Holy Cross College measured 104 miles an hour, 1998. I think that was part of a squall.
The Brockton storm, it was isolated, but it sort of formed a mini bow, as we call it. It was an individual storm, but it actually did bow out a little bit as the straight line winds fed through it. We got 104 there. And then, May 31st, 1998, that was a massive outbreak, and coincidentally, we had an open house at our office while that was taking place. What a way to go. The squall line went through Worcester at Holy Cross, and they measured 104 miles an hour. As Glenn mentioned earlier, straight line winds have been measured as far up as 175 miles an hour.
I remember a midnight shift, I forget what year it was, back in the mid-1990s, also in July, where we had what's called a derecho, which is a really fast-moving squall line, that just as we came in at midnight, Severe Storm Center was telling us they're going to be issuing a watch probably around 3 o'clock. And I said, why? There's nothing on the radar in the northeast states. It was actually from a system out over the upper peninsula of Michigan. And it was racing more than 120 miles an hour. And it was, sure enough, by 8 in the morning, it was off the New England coast. That caused 94-mile-an-hour winds, I remember, in Otis, not Otis Air Force Base, that was Otis in Berkshire County, and weakened as it got to Worcester. But another example of a really fast-moving squall line. They happen a lot around New England.
Okay, so only in Oklahoma can we see it not just on radar, but someone was actually able to take a picture of it, a picture of something similar. Here's your shelf cloud. You are north looking toward the south. West is off the screen over there to the side, and east is over here to the left of the picture. Here's your shelf cloud, and we had a downburst within the line. One of the elements, the winds pushed out a bit stronger, pushed that one part of the line out ahead of the rest. So here's your bow, right there, and the strongest winds right there at the head of the bow. Now we actually have a picture, actually a little movie loop here from radar of a squall line in progress. You can see how it's lined up like that. Now notice right there, this light blue. That is, as we saw in the other radar picture, that is the leading edge of rain-cooled air. And you can see how it goes through Ponca City. In fact, if we back up for a moment here, there's 9:30 p.m. It reaches Ponca City. And then 10 minutes later is when the leading edge of rain gets to Ponca City. So there's actually a 10-minute gap between when the winds went through and when the rain and hail went through that spot. That shows you there is typically a gap between the wind, which leads the storm, and then the rain and hail, which comes after. Okay. Now back to the storm. So the squall line. This is a big severe weather producer here in New England. Produces strong winds, large hail. It can produce weak tornadoes. Location. Straight line winds. You're going to find those on the leading edge of the storm, under the shelf cloud. In fact, that's a key 3-letter phrase, 3 little words. Under the shelf. Under the shelf. That's straight line winds. With squall lines, any potential severe hail would be in that rain area behind the leading edge of the storm. So squall lines, first the wind, then the rain and hail. Okay, that's 3 types of thunderstorms. Here's the 4th, the supercell. And this is one huge thunderstorm complex where the single cell might have been 5, 6, 7 miles in size. A supercell can be 30 or 40 or 50 miles in size. I once measured it on a radar image out of Oklahoma, and it showed a supercell that covered a whole county with room to spare out there in Oklahoma. And because of its size, because of its ability to maintain itself over several hours, these can be extremely powerful. And this pilot definitely has the right idea in giving this storm a wide berth. Here's a diagram of a supercell. As with all thunderstorms, you have the thunderstorm updraft, supplying the warm, humid air, which is typically pumped in from the south, or the southeast, or the southwest, but generally from that southern half of the sky. It's pumped in, and drawn up the updraft, and where the water and ice collect in the upper part of the updraft. With a supercell, though, there are sufficient winds aloft so that unlike that single cell or pulse storm, all of this water and ice is pushed out of the updraft so that it doesn't have a chance to really collect a lot and become so heavy that it collapses down through the updraft as with the single cell. Instead, it's all pushed off to the north and northeast, and where it falls as rain and hail. And because it falls to the north and northeast, it's not interrupting that flow of warm, humid air, so the updraft keeps getting fueled. And the downdraft keeps raining, so you get this continuation, this updraft, downdraft. It just continues to cycle on and on, hour after hour, allowing the storm plenty of time to grow in size and strength. Supercells, when viewed from far away, you're going to see mainly just the very top of the storm. You're going to be looking for an overshooting top, something especially that may persist for 10 minutes or more. And how sharp, how well defined is that anvil? Here's a picture of a supercell. There's the main storm tower carrying the water and ice aloft. Hits the top of the lower atmosphere, and all that stable air at that point. The upper winds throw or push the water and ice downstream. You get that anvil top that extends downwind a strong ways. And if the updraft is sufficiently strong, it may actually punch its way through that anvil and up into the stratosphere, forming this dome, which we call an overshooting top. So a main storm tower, anvil, overshooting top. The key features in identifying a supercell from far away. Now, as they get closer in, your ability to see the upper part of the storm is going to disappear. The storm is going to be blocking your view. You're going to be focusing more on the underside of the storm, especially the underside of the anvil, where that updraft is, not the anvil, the underside of the tower, of the main storm tower, where the updraft is so strong, rain can't fall back through that updraft. So the base of that cloud is rain-free. And in fact, there may be a portion on that rain-free base where a part of the cloud actually extends its way downward, closer to the ground, forming this thing we call a wall cloud, a part of the storm that is closer to the ground than the rest of the rain-free base. Look for it to persist, the wall cloud. Look for the wall cloud perhaps even to start rotating, a sign of certainly some significant problems. Here's your rain-free base, the updraft keeping the rain aloft so there's nothing falling underneath. And then over here, off to the north and east, out of the updraft, is where you have your rain and your hail. This particular picture, you typically might be, in this case, to the west, to the east or southeast of the storm, looking toward the west. If we zoom in, we can sometimes see this particular part of the rain-free base that is actually pushing itself further down, closer to the ground. It is still a part of the rain-free base. This is not a scud cloud. This is not some separate cloud underneath. This is all part and parcel with the rain-free base. And size of this could be several miles across. So notice too, this is sort of pointing toward the rain and hail, which is off to the north and northeast. The wall cloud, it occurs with the supercell. It occurs on the southwest trailing side of the supercell, and it points toward the rainfall. Now that's sort of the exact opposite of what we discussed with the squall line shelf cloud. The shelf cloud is with the squall line, occurs on the leading edge of the squall line, and points away from rainfall. The wall cloud is on the southwest trailing side of the supercell, so it's trailing side of the supercell, and it points toward rainfall. It's a study in opposites, and that's a major way to be able to tell the difference between the two. If you just suddenly woke up in the middle of a thunderstorm and didn't know where you were in it, that is one way that you would be able to tell.
And again, the wall cloud is in the updraft portion of the storm here. It's hard to understand how something descends in the updraft region. But sometimes in the Midwest, you can actually see that rain off in the distance gets sucked back into the wall cloud, sometimes known as a tail cloud. But anyway, that just proves to you that is an updraft region, and it's a lowering of the rain-free base in the updraft region.
Why do we get these differences between thunder? Why don't we just have one generic type of thunderstorm? Well, it's because of the winds aloft. If they're weak or if they're blowing in every which what direction, you really don't get that much organization, so you end up with those single cell pulse thunderstorms that don't really live for too long, but even so, they usually don't have the strength of the others. If the winds line up in what amounts to a straight line through at least part of the atmosphere, that tends to organize those thunderstorm cells into the straight line, and we end up with a squall line. Or if you get the winds blowing sort of like the way Glenn was discussing earlier in giving you one of the cases for the tornado, with the southeast winds or south winds near the ground, clockwise turning with height so that you've got winds blowing from southwest to northeast higher up and picking up in strength too, 45, 50, 60, 90 miles an hour. That kind of organization is what's needed to keep that updraft and downdraft in the supercell separate, and for that matter to have all that rainfall take place in a location that doesn't interfere with the inflow of the warm humid air. Speaking of strong winds, you can sometimes tell it just from looking at the clouds. Here's one updraft. Instead of going straight up, it's sort of bent over on its side a bit. And that's those strong winds blowing the top of the updraft over a little ways. Meanwhile, this updraft, well, he don't care about no stinking winds. He's going to go exactly where he wants. Straight up. Straight up. And in fact, he's so strong that even punches through into the lower stratosphere, causing this overshooting top right there. Now, which direction are the winds blowing in, do you think? Well, take a look at the anvil of this storm. Where's most of the anvil? It's over here. So that the winds are blowing, I mean, there's not much over on this side, so the winds are blowing across, right to left, maybe a little bit into the picture too, but left versus right, left to right versus right to left, it's clearly right to left. Here's a diagram showing those the updraft, and those strong winds just blow the water and ice out of the updraft where it falls to the north and east. The heaviest stuff is going to be the first to fall once it gets out of the updraft. So the large hail will fall first, smaller hail after that, and then the rain would be further on. In fact, if we take a look at an overhead view, you can see here's your updraft. As you get out of the updraft, the first thing to fall out will be the heaviest objects, the large hail, then the small hail, and then you get into the rainfall. It sort of organizes the storm, the precipitation from the storm. So if someone were up here and the storm were moving toward them, they might get a shot of wind from the outflow of rain. Then they'd get into the rain would get heavier and heavier, and then it would shut off completely. It would get into some small hail, increasingly larger in size until it shuts off, and then you're underneath that main updraft right there. Now sometimes these storms rotate. When they do, that could draw some of the precipitation around to the west and southwest side of the storm, forming this little hook shape. In fact, when we see that on radar, that's exactly what we call that, a hook echo. And taking a look at an actual radar picture, we see there's your hook echo right there. Increasingly heavy amounts of energy being reflected back to the radar until you get to this point when suddenly there's nothing right there. Hey, storm's over, right? Not exactly. At the time this image was made, an F5 tornado was tearing through the south side of Oklahoma City, including the suburb of Moore, Oklahoma. It was May 3rd, 1999, and a portable Doppler radar on wheels, which was measuring the tornado that was in this location, measured a wind a little ways above the ground of 318 miles an hour. One of the strongest winds ever measured. And you can see, typical supercell with the hook right there. Supercells, strong downburst winds, hail of any size, tornadoes of any size and shape. A location. You might get a downburst wind out at the leading edge, but if you do, that's just the appetizer. Most of the action is on the southwest side, some hail near the edge of the, large hail near the edge of the precipitation, possibly a tornado underneath that southwest trailing side of the storm. Important point, important operator's point. These supercells are rare in New England. We might get one or two a year in the entire region, if that. But when they do occur, there's a high likelihood of some form of damaging weather, whether it's wind or hail, maybe a tornado, but certainly some form of damaging weather, high likelihood. Now, there are some days when it's very easy to spot because the clouds are going to tell you right away what they intend to do. I think we put our finger on the problem, Glenn.
Cumulus fingerus.
Yes. Quick review. National Weather Service, SKYWARN. We are part and parcel. SKYWARN is organized by us in conjunction with amateur radio and a couple of other organizations as well. Civilian volunteers reporting their information to us. Thunderstorms generated by those ice collisions in the thunderstorm updrafts has 5 different types of hazards, each of one of which can be dangerous. We also have 4 types of thunderstorms: the single cell pulse, the multi-cell, the squall line, the supercell. Which one we get depends on the organization of the winds aloft, something meteorologists are looking at each day. Supercells are rare, but dangerous when they do occur. Okay, congratulations, you have made it through halftime.